Good morning, good afternoon, everyone. I'm Huangwei from National University of Singapore. So this is the pre-conference webinar for the 15th Asia-Pacific Conference on Combustion. So today, the topic of this webinar, it is ammonia and hydrogen for power. So at the beginning of this webinar, I first would like to introduce the ASPEC. So ASPEC, it is a regional conference sponsored by the Combustion Institute. The first ASPEC was held in Osaka, Japan in 1997. So this conference has now become a key stage, for the to emphasize the importance of the regional collaboration and the exchange of scientific knowledge in combustion and technology. The ASPEC is held every 2 years, and its location rotates among different CR sections in the Asia-Pacific region, including China, Japan, Korea, Taiwan, India, Saudi Arabia, and Australia. So in 2025, the ASPEC will come to Singapore with some new changes, including ASPEC paper publication in Proceedings of the Combustion Institute. This will be hosted by the Singapore section of the Combustion Institute. So the ASPEC 2025 will continue to be a vital forum for the combustion research community in this region, featuring a diverse range of topics and attracting participants from both academia and industries. So with the theme of building a zero carbon and sustainable future, the ASPEC 2025 will be significantly advancing research on decarbonization, promoting sustainable combustion technologies, and fostering regional and global collaboration to address the challenges of climate change and environmental sustainability. So for today's webinar, we are very happy to have two speakers, Dr. Ghenadie Bulat from Siemens Energy and Professor Agustin Valera-Medina from Cardiff University. So before the presentation, please allow me to introduce them first. Dr. Bulat is the head of new technologies for gas services at Siemens Energy, where he leads a global team of highly qualified experts. He drives the innovation and excellency in all disciplines required for the success of products of the future. Dr. Bulat joined Siemens Energy in 2003, but his experience includes more than 20 years of engineering and management within product development and technology innovation. Dr. Bulat obtained his PhD from Imperial College London and his engineering degree from Technical University of Moldova. He is a chartered engineer, a member of Institute of Mechanical Engineers and the Combustion Institute, and a visiting professor of combustion at Imperial College London. Professor Agustin is a professor from Cardiff University in UK. He has participated more than 30 industry projects with different industry partners, such as Rolls-Royce, Siemens, Ricardo, Airbus, and EON. He has published more than 230 papers, and 70 of these specifically focusing on ammonia power. Professor Agustin's contribution to the Innovate UK project, decoupled green energy, from 2015 to 2018, which aims to demonstrate the use of green ammonia produced from wind energy. He is currently the PI of different ammonia-related projects to demonstrate the use of the chemical in power and heating. Professor Agustin is co-director of the Institute of Net Zero Innovation, Cardiff University director of the Center of Excellence on Ammonia Technology. We call it CEAT. He is also a fellow of the Learned Society of Wales. So next, we will invite Professor Agustin to give you a talk. So after the talk, we will have around 20 minutes for Q&A. So to the audience, if you have any questions you want to discuss with our two speakers, you can submit the questions through Q&A in the Zoom meeting room. Okay, Augustine, now the time is yours.
Thank you very much, Huangwei, and thank you very much for that interesting presentation, Gina. Thanks everyone for joining us. So I'll be talking about ammonia for boilers in rural locations. This is work that has been sponsored by the Department for Energy Security and Net Zero in the UK and is in collaboration with Flow Gas, a propane company, and ERM consultancy here in the country. The use of ammonia is a very interesting one. We've been pursuing it. For those that know the work that we've been doing here in Cardiff for some time now, it's almost 11 years. As presented by Gina, this is something we started with them. And now we're progressing into the use of the combustible ammonia for other applications, not only gas turbines, but also boilers, internal combustion engines, furnaces, etc. And the whole rationale goes back to this analysis done by the Hydrogen Council. So what they did was to evaluate all renewable sources that you can see on the left, on the top, green highlighted, and it's essentially everywhere in the world we can then tap some photovoltaic wind energy, and it's not in there, but also potentially marine energy, compared to what we can do with, for example, natural gas that is very localized. So with that, the Hydrogen Council and many other councils, government bodies, or associations are looking into the use of hydrogen as one potential to then move around and that renewable energy. And as part of that analysis, what they did in 2021 was to evaluate the mobility of energy produced via renewable energy and then convert it into hydrogen to then deploy it to places where it's going to be needed the most. So, for example, they evaluated 3 cases: Chile to the US, Saudi Arabia to Europe, and Australia to Japan. And with that, 3 different vectors: ammonia, liquefied hydrogen, and liquid organic hydrogen carriers. As you can see at the bottom, from clean production to the final cost at port, all of them are barely the same: 3.2 to 3.8, $4.4 per kilogram of hydrogen. Now, one of the parts that is very interesting is that if we remove from ammonia the part of cracking, and then that becomes almost 2/3 of the most cheap option, that is liquefied hydrogen, therefore making ammonia the best solution for these processes. Another thing that is very interesting is that as part of this levelized cost of electricity that has been analyzed and promoted to then see what is the most versatile, most economic solution, there are a lot of works around in now the literature. One of them, this one, produced by the University of Minnesota in 2020, where they evaluated the use of hydrogen or ammonia, or a combination of both, for all these different cities in the US. So depending on where these locations were at the time, if they were close to an offshore wind facility, then it would be then more on the scale of hydrogen deployment. Whereas if they were in the middle of the country where they have an ammonia pipeline, then ammonia would be the most suitable solution. But combining both gave, in all these scenarios, the lowest cases, the lowest cost of electricity. And that's because you can reduce the capex on both systems, the hydrogen producing units, and also the storage of ammonia. So therefore, it's a combination of both that is going to be the most conventional, they probably prefer in the following years. So you can use directly hydrogen that is produced in fuel cells, cars, or other applications, whereas if you need to then store any surplus, you can do it via ammonia and eventually use it directly, as I showed, then avoiding the conversion back into hydrogen. One of the questions that I always get is, where are we going to get all this hydrogen from and all this ammonia? And then this shows very nicely all the different technologies that are now in trend and that are now people looking at for the deployment of this ammonia. And we are now running on what is generation 1 that we are using by steam methane reforming. We recover the hydrogen and then dump loads of CO2 into the atmosphere. That is now progressing into what is generation 2 type of systems with all this renewable energy, as mentioned in the previous slide, that eventually can then put into a Haber-Bosch system. That is the method of producing ammonia. We recover some nitrogen from the atmosphere, put them together with the hydrogen, and therefore we get the final ammonia, and therefore we don't produce as much CO2. But then the third one is via electrochemical process processes where we are going to combine then water and nitrogen straight away, even air, and therefore producing the ammonia without having to go into high pressures, high temperatures. And once that happens, what that means is that everyone in the planet, anywhere, as long as you have air, water, and energy, then will be potentially capable of producing their own ammonia, which again opens all the opportunities and can then be the breakthrough of energy for the future. So about that, we have the production of ammonia, all these different methods. We have talked about green, we have mentioned about the use of steam methane reforming. We have the cases of steam methane reforming where we can sequestrate the CO2 and therefore put it on the ground and then produce what is called blue hydrogen, or even something that is pink hydrogen or pink ammonia that comes from nuclear reactions. So all this is going to be now part of the hydrogen future, and obviously the production of ammonia that, as shown, can be the method of deploying all this amount of energy. But however, when it comes to the use of ammonia as an energy vector, we have several restrictions. We have spotted over the years 4 of them that related to first the production without carbon production. We need to have cost reduction and efficiency improvements in those type of systems, power generation at utility scale, and also heat production with stable low emissions, public acceptance and safe regulations that are required everywhere because we don't have any when it comes to the use of the molecule as a fuel. And then finally, the economics that obviously need to be profitable. And with that, one of the areas that we have pursued is power generation, heat generation using ammonia. This shows some of the opportunities and places where we can spot the use of this vector. And as mentioned before, and done by the Hydrogen Council, is that ammonia can be deployed in city gate terminals, locations close to the ports, and then eventually converted into hydrogen to then be fed into cities or the natural gas grid. Now, another area that we have identified that we believe is going to be the one where ammonia is going to rule is rural locations. And the reason for that is that these locations are off-grid. They don't have the same infrastructure for electrical connectivity. The delivery of hydrogen via long or massive pipelines is not economic. They already using fuels that can store some of this energy, for example, propane, butane, etc. And there's another component that is the public perception. People are used to the smell of manure. So as long as the concentrations of ammonia are not high enough, then people, again, smelling that chemical, they know what it smells like. So that's the reason, because rural locations spread all across the world can be the location where to do it. And when it comes to, for example, what Gina mentioned, stationary large power, these type of units are in the countryside. So again, it just opens the opportunities for heating, cooling, stationary power, and then heavy duty transport using the chemical directly. So along those lines, we have been doing this project that is, as I mentioned, in collaboration with Flow Gas and ARM. And initially, we conducted some techno-economic analysis. The results were very promising, because they showed, first of all, in terms of emissions, having green ammonia will bring down the emissions of CO2 drastically compared to what would be the current fuel that they're using at the moment in these locations, propane. So as you can imagine, again, the amounts of kilograms of CO2 that we'll be saving are in the lot, around 170, 200 kilograms of CO2 that we will be saving by using ammonia in locations that are currently operating on propane gas. Now, one of the things as well that is very interesting is that when compared to liquid hydrogen in these locations, ammonia was even better in terms of the economics. And the reason for that is that instead of bringing 3 North tanks of hydrogen, or 4 or 5 that will be required to then power these locations, we would bring only 1.5 2 of ammonia because of the energy density that you got on ammonia itself. So therefore, in terms of replacement of LPG, this was the best solution. LPG also shares a lot of commonalities and features with ammonia. Can be stored at -33 degrees compared to -42. The components for evaporators, stainless steel, are made for LPG and can be used as well for ammonia. Delivery lines, etc., they just all fit in line to the use of ammonia and replacement of LPG. So with that, we are now commissioning a large system. Is a knowledge that we have gained over the years working with Tata Steel, the South Wales industry, with Siemens. And with that, we obtain a Department of Energy Security and Net Zero proposal, and finally a project to convert a boiler of 1 megawatt into ammonia fueling. So with that, we have been working on several concepts: fuel stratification, temperature control, integration of systems, cracking of ammonia, hydrogen sieving, artificial intelligence, advanced computational design, bespoke storage and delivery, etc., to reach that 1 megawatt. And with that, what we are now planning is we got new patents, we got novel feeding systems, control strategies, cracking devices to then provide us with large academic and commercial dissemination for flow gas. It is commercialized and envisioned that if the systems operate as we are planning to, this can then spread over around 700 millions of revenue for the company in the next 15 years, with the production of around 70 direct jobs and the novel creation of ISO standards. So what we here obtain in terms of combustion is that as part of our first phase analysis, we obtain and design a burner that is capable of minimizing to almost negligible values the NOx emissions. Now, as those operating and using already ammonia, you might know that there's a trade-off between some parts per million of ammonia versus nitrogen oxides. In this particular component, the trade-off is quite good. We are below around 20 parts per million to zero nitrogen oxides, which is fantastic, around 15, 20 kilowatts power. And this is because we are using a method of stratification of the hydrogen that we obtain via cracking and the ammonia that we're injecting as a premix part of the flame. Now, that first phase has delivered what is our second phase that is in line with the 1 megawatt power unit. And as you can see, we are now obtaining results in terms of crackers that we got in situ. And we are now testing different materials, ruthenium, nickel base, to then see what are the properties at different flow rates in situ and online with what is our flame and heating process of thermal crackers that we're using and improving as we go along. Also, we are doing thermoacoustic analysis on the different flame patterns that we got, testing with pure blends of ammonia hydrogen and blends that have now cracked ammonia. That includes the nitrogen itself. As you can see here from the thermoacoustics, they change. They are very different between themselves, and something that, again, is just prompting a lot of interest in terms of research we're doing. Some other components, radiation, that is at the top as well. We're evaluating how radiation with the different blends is actually acting on these burners. And with that, we're integrating artificial intelligence to then determine the new reaction mechanisms and new methods to then control our feeding systems. So all that is part of what is our fundamentals of this type of program. All is going to be presented in the third symposium on ammonia energy for those that are going. Now, when it comes to the commissioning of the system, what we got is all these units is a 500 kilowatts power unit that eventually going to be replaced by a boiler of 1 megawatt. And we got large drums of half-ton of ammonia evaporators that can deliver those conditions of half a megawatts power, propane that is used for the transition of the flame, with a control system that is fully dedicated to then use these fuels. The way that we are doing, as I mentioned before, is artificial intelligence based. So we are looking into the chemiluminescence of the flames to then determine equivalence ratios and power ratios of the flames that we're using. So that way we're feeding back and then finally controlling what we see and what we obtain, and finally NOxes that will be important to address as well. With that, we have done the commissioning, control systems, artificial intelligence, bespoke protocols, analysis of hazards, and also operability studies and dispersion analysis. And with that, we have done as well advanced modeling to improve what is the reactor and the burner itself. It's interesting because we have done around 200, 250 different models in collaboration with the University of Poznan. And with that, some dispersion analysis that show, for example, in this case, that if that drum that I showed you half a ton, then suddenly it has a massive spill and all the ammonia is just spread everywhere, it will then reach around a 250, 300 meters radius of the center of Cardiff, which means again we'll have to evacuate all town, which obviously we don't want, but that's what you get when you're using a component like ammonia. Now there are a lot of risks associated with that. With that as well comes a method to then mitigate these issues, but this has been part of the program. And with that, we got now a HACCP's dispersion analysis. We have done 300 kilowatts facility Cardiff commissioning, and we have run our tests with CFD modeling and acquisition of new measuring systems. As we are now progressing, we are doing 300 to 500 kilowatt tests just these days, develop bespoke ammonia delivery units, novel fueling controls, and we're working now on the potential of having a technical specification for this type of units with evaluation of novel methods for emissions control. And what we are planning now in the next 2 months is to then test at 1 megawatt technical specifications that can be put forward to the ISO committees and demonstrate the unit in 4 weeks, for 4 weeks, continuous operation in a final user facility. And with all that, it wouldn't have been possible without the support from DESNES that gave us a total funding of around 3.5 million pounds to conduct all this. So just to wrap it up, these are some of the analyses that we have done in terms of risk assessments, and obviously HACCP and HACCP studies to then conduct all these evaluations. Further, some literature review that shows the complement of using either LPG, gasoline, or ammonia in fueling stations, and how the case of ammonia is even better than the case of LPG. And that's because once that you have some spread or leak of ammonia, then the time that it takes to start converting back into gas is massive. Plus, again, is very highly detectable. So in these type of scenarios, could be even better than the LPG cases, and because of its explosivity that is massive in the case of LPG. Similarly, some other studies done by the US government show that fatalities when it comes to ammonia are minimal over the last 15 years. Now, obviously, this is when comparing refrigerants or fertilizers, not fueling. That changes the name of the game. So therefore, we need more research in this area. So the conclusion, ammonia can be used for power purposes via combustion. Green ammonia produced from renewable energies is capable of storing some of these stranded energy. Rural locations are a preferred option for the chemical for direct fueling applications. Fundamental analysis shows stable regimes, whilst the potential of in situ cracking improves combustion features, and robust developing complex integration and advanced modeling have served us to then establish these facilities. Now, one of the things that I would like to raise is that the idea is that during NASPAC, we'll present the combustion results of all these facilities. So you will be able to see 1 megawatt power fuel burning ammonia hydrogen flames via cracking methods. And that's it from my side. This is my team. And if anyone is interested in ammonia, we have a symposium. ASPAC is now a partner with us in this venture. So thank you very much. And yes, open for questions.
Thank you very much, Agustin, for your insightful talk, and show us lots of exciting research progress for ammonia used for power. Yeah. So next we will have some time for Q&A. So if you have any questions, you can submit the question through Q&A. Yeah, Asad has question. Maybe Lily, you can invite Asad to the panelist.
Thank you, Huangwei. Just a reminder that we're taking questions via text, so we invite Asad, please, to share your question via the Q&A if that is possible.
Yeah, or maybe you can unmute Asad so he can directly ask the questions. Yeah. Hello, Asad.
Can you hear me?
Oh, yeah, very clear.
All right, good. So thanks to both Bulat and Agustin for very nice presentations. I've just got a question, maybe one for each. The first one is for Bulat, if I may, and that is, on your RQL combustor, I was observing your profiles of N2O there in the combustor, and I didn't quite make sense of that. I was wondering if you could elaborate on this, as why the N2O is there where it is. If it is a genuine RQL, I would have thought that it should be the peak N2O should be downstream in the lean parts of the combustor, but it seems to be, at least to my mind, in the wrong region. Can you explain that, please?
Yeah, absolutely. Thank you, Professor Mastri, for your interest in this. Actually, what we have done is we looked at, if I can share the screen, perhaps, we looked at this technology based on SGT 750. So we use the existing architecture of the combustion system, and what is not shown in here, we have a rich queen lean small burner right here that is injecting the fuel. So
can't see, Bulat. Can't see what you haven't shared the screen.
Oh, I'm sorry. Thank you. I'll try again. Tell me when you see it.
Yeah.
So yeah. Okay. So where we are today, at the moment, for natural gas, we have a pilot reach zone. So we call it RQL pilot that is in here, and we replace that pilot with just fuel injection. And then we run the combustor as reach environment, and then we have some quenching later in the system. But we haven't included the quenching system in this simulation. So we really looked at, as you pointed out, really looking at the NTO formation in the primary zone without the quenching part in here. So that will come next. Yeah. So we just started to put this large LES analysis into the configuration of the actual combustor without the reach burner or pilot burner, and without the quench part as well. Yeah. So to some extent, yes, a very valid point. The NTO is formed in the primary zone, but is not consumed with the injection of the O2. Does this answer your question?
Yes, it does. No, so that's not the it does.
Yeah, thank you for that.
Thank
you for the question. Nice to hear from you. Hope you're well.
Same here, and look forward to seeing you in Singapore, I guess, right?
That's right, yes.
And Agustin as well. Hi, Agustin. My question to you, Agustin, is regarding your super low levels of NOx there, 20 ppm. Interested in that. I was just wondering, what brought that about? Was it burner design, or was it a combination of burner design and fuel blend? And the follow-up question is, since we're talking about N2O as well, what is the level of N2O?
Yeah, no, thank you very much, Asad. Hope you're fine. And yes, hope to see you as well in Singapore. So yes, to that is a combination of both. We did some analysis again over the past and some of the initial work with Siemens on trying to then find what would be the most stable, lowest emission blend that we could get. And that's when we came up with that 70-30 blend that you've seen there. And that's the one that is giving us the best profiles, lower instabilities, better performance, etc. So with that, we start looking into then the improvement of the geometry. So the geometry would allow to then increase the residence time of some of the species, especially the NO, as we're increasing the interaction with NH2. And that would then lead to then the production of more nitrogen water content. When it comes to N2O, because we're running slightly rich around 1.1 equivalence ratio, the values are 0. It's the onboard ammonia that we still have there. But because we are then increasing that residence time, then at the post-combustion zone is being reduced. So both the NO and the onboard ammonia, they reduce each other.
Nice, nice. Good work. Thank you. Thanks to both.
Thanks, Asad, for your questions. Thanks. Any other questions? If you have any questions, you can submit through Q&A. Okay. Yeah, maybe ask one question to Gena. So in your presentation, you mentioned 3 different technical routes. So the first one is fully cracked, and then partially cracked, and the last one is direct combustion of ammonia for power. So what is your view about the prospect of these 3 different technologies for industrial applications in the very near future?
Yeah, I mean, that's a very good question. Thank you, Professor Zhang. Yes, the prospect, it really depends on the application. So, for example, if we are in Singapore, then definitely for Singapore, direct ammonia combustion is significantly more attractive, mainly because of the land required for cracking and the fuel treatment of fully cracked ammonia. So, for example, you need a significant amount of land for that. If we are to say we are in the port of Rotterdam and we are importing ammonia via marine, and we do have the ability to have cracking on site at the port, then yes, fully cracked option for Europe may be an option. Is quite attractive. And European hydrogen backbone is actually relying or considering that as an option to have fully cracked at terminals and then inject hydrogen into the hydrogen backbones. That's an option where you have space. From our perspective, we want to connect the energy conversion machines like gas turbines to support either direct ammonia or fully cracked. The partially cracked part is actually very interesting for the smaller units, below 100 megawatt, because then you have the ability to really integrate and get the best efficiency of the whole plant for using the heat from the exhaust of a gas turbine to crack the system and put it back in. We saw that in Agustin's presentation as well, and we're happy to share some of our work in the next conference in Singapore.
Okay, thank you very much. So my question to Agustin, you showed some very interesting results about the integration of the cracker and the combustor. So what is the overall efficiency from your system? This one question. Another question is, I think because this is a slow burner, I think laboratory scale burner, right? So the exhaust, the energy or the temperature actually will be much higher than real gas turbine system. So what is the gap, between your laboratory technology and real applications? Like for efficiency, NOx, and what is the composition of the cracked gas and so on?
Yeah, so when it comes to the efficiency, we are now doing the test, and depending on the material that we're using, as you could see, again, we got different cracking percentages. So we're now evaluating that. Hopefully in the next 2 weeks, we'll have those numbers to present them in Shanghai. But theoretically, what we have estimated is that out of the 1 megawatt will require around 90 kilowatts for cracking. Again, that would be just the theoretical number, which again, say we have a cracker that is efficient at 50%, that will go down to then 160 of the total 1 megawatt that we'll be producing. So around 85%, which is somewhere around, again, boiler efficiency, which is not bad at all. Now, again, I'm just making up these numbers. We still need to then assess and calculate properly. In terms of the application, we are now in the process of installing the cracker at larger, in the larger facility, and that is going to pass around 12 grams per second of ammonia. Now, as you could see, again, the system that we got, the 20 kilowatts is working fine. The one that is at 1 megawatt, we'll need to then see if it works. So yes, it's something that now is in the line, and hopefully I'll be able to present in Singapore. So that's the idea, to then present those details there.
Okay, thank you very much. Yeah, actually, from the latest symposium in Milan, we already, saw some papers, working on so-called ammonia pyrolysis in the combustor. Somehow it's like in situ, cracking. So what is your view, between this technology and the integrated system? In that case, actually, the cracking, it is in a separate reactor, right? So what is your view about these two different technologies for ammonia cracking?
Yes. Then I believe that I have seen it also. I have seen it in the ASME conducted by the groups in Saudi Arabia, which is really interesting. Yeah, it's very, very nice. And I believe it's a potential way forward to then reduce components. Now, the good thing about having the additional reactor is that you can then have more control on the cracking rather than actually have it via direct flame. But it's something, again, is still to be seen. I think the main issue is that we still are understanding what are the implications of having the reaction of nitrogen when it comes to all these different temperatures and the production of different products that could then lead the potential of even some unborn species, NO production, that again, when you have a separate system. But yes, I mean, it's now, I think the name of the game is what now people are working on, cracking technologies to then use ammonia.
Okay, thanks. So any other questions from the attendees? So you can submit the questions through Q&A. I think we can still take. Okay, Assad have another question. Yeah, maybe Lily Chabio to invite again. Yeah. Hey, Assad.
Only if there are no other questions from the audience. I don't want to take other people's turn.
Yeah, please.
So my question is to Ghenadie, if I may, and that is regarding, I saw on one of the cases you showed a liquid ammonia.
Right.
So maybe if you can comment there about the, liquid ammonia flashes inside the combustor, depending on what conditions you feed it in. You've got a very low temperature region there. Just wondering about the management, the thermal management and the ignition management there in those regions. If it's been a problem, you want to comment on that, Ghenadie.
Yeah, this is definitely an area of research, and we are counting a lot on our academic partners to help us with that. Yeah. So we are very good at burning fuel in gaseous form, and we are really good also burning liquid fuel, especially conventional liquid fuel. And we're seeing the efforts that our cousins in the aerospace industry are looking to move towards more renewable fuels, liquid fuel. Now, liquid ammonia in general is something that we are exploring, but we are exploring it from a power plant perspective first. Yeah, so pumping it and then injecting it into a combustor is that giving us an overall power plant benefits. So do we get benefits in terms of actual power or efficiency or not? So we're looking at it from the macroscopic scale, then we will go down into the details of designing the system. Now, pumping liquid ammonia has benefits, but as you said, also has drawbacks, and it will have an impact on the combustion system architecture. So we are looking at it, as I've said before, really going into starting to do detailed design of the system. We really wanted to ensure that there are benefits that can step above gaseous ammonia injection. We have seen the benefits of gaseous ammonia injection, of course, as I mentioned in the, but that also has the requirement on the vaporizer, which will have an overall power plant point. So as an energy, fully integrated energy and transition company, Siemens Energy will look at really converting electrons to molecules, molecules back to electrons, so in the most efficient way at the power plant, not only at the conversion point. So when we get to design the combustor specifically for the liquid, then we will look at details of aspects that you mentioned, Professor Matsuri. At this point, what I presented on that slide 9, it was really based on overall performance, integration, and plant assessment. I hope that answers your question.
Yes, thank you very much. Thank you.
And if you do have any suggestions, or if you are working in this area, please do let me know. We are looking, and we are exploring, and we're learning from our academic partners in this. So maybe we can use the conference in May next year to highlight what options are there for burning liquid ammonia, if that is something that you are interested in.
Thank you. Thanks very much.
Okay, thank you very much. Is there any other questions? Okay, so if no more questions, please join me thanking our 2 speakers again. Okay, thank you very much, Ghena and Agustin.
Thank you.
Thank you very much.
Thank you everyone and join us the first pre-aspect webinar, and our next webinar will be in middle October. So the topic of the next webinar will be AI for combustion and energy. So stay tuned. Okay, thank you. Bye-bye.
Thanks everyone.